In many classrooms, teachers rely on lectures to introduce new concepts to their students.
I think a lot of people can appreciate that as compelling and interesting as a lecture could be, it's not the best tool that we have for communicating understanding.
Advocates of a physics instruction method known as modeling, like high school physics instructor Seth Guignols-Kupperman, want to spark students' curiosity with an approach that emphasizes investigation and discovery and makes students more responsible for learning from each other.
People don't, in a deep sense, they don't learn by being talked to, right? So in a modeling style, instead of starting with a conclusion, you actually ask a question. Or you say something like, what can we find out about a ball that's falling? And you investigate. They don't even know the answer to it until they're done with the experiment.
In physics instruction, modeling employs a teaching method known as interactive engagement that Guignols-Kupperman seeks to master in a study group facilitated by physics education professor Ferdinand Brunschwig.
Well, interactive engagement is a way of connecting with the student so that the student actively participates, thinks about the subject on his own, and where the communication is a two-way street. It's not a one-way street. In fact, it's a many-way street where you get the students to interact with each other.
Using modeling, Guignols-Kupperman has transformed his classroom into a place where students can learn by emulating the way scientific discoveries are really made.
In a modeling style, what you're trying to show your students is that all we really understand of things is a model that we put on them.
The models are what you're aiming for. The models are the ways of thinking about the physical world. It can be a picture that you have in your mind. For example, we think of the sphere model of the Earth. The Earth is a big ball. Well, the Earth is not a big ball. The Earth has all sorts of bumps on it. The Earth is uneven. But for a very good approximation, we can think about a sphere as the model for the Earth.
This gives students the opportunity to learn in an environment that simulates the world of scientific discovery.
We can put every force through a test and say, if we can identify who's causing the force and we can identify who the force is acting on, then the force exists. Modeling, or at least in this style of instruction, we begin with the investigation. All right, I'm going to draw an exaggerated diagram of the Earth. And then as a community of scientists, we see a phenomenon, groups of students investigate the phenomenon, and they all pool their results. And an instructor coaches students through that so that they can have that discussion.
And the tool the teacher uses to emulate the discussion part of scientific inquiry is the whiteboard.
That's a very important part of it, that the students can write their group results on, and it helps them to communicate and to interact with other groups and to develop these conclusions to lead them toward the models.
That's a big piece of how I set up my classroom. I'm going to give every group a pair of odd problems or a pair of even problems. So you with your partner are going to do either 1 and 3, or you're going to do 2 and 4. Usually as a teacher, you have students working on a worksheet or working in their notebooks. It's very private and isolating. Even if you have students working in teams, it's still all located in their little world. But if you allow them to use a whiteboard, if you also only allow them one marker so that they kind of have to pass the talking stick around, it forces the conversation.
It's an acceleration when it's coming up as well as when it's coming down.
So instead of being isolated, they now are dialoguing, and they're sharing that experience on a single problem.
So, let's draw it. Since we're not allowed to write on the paper, no pencils or pens.
Draw the diagram?
You're neat, right?
Yes.
All right, let's go.
There's always an acceleration. Due to gravity, right?
Yeah.
Alright, I'll draw the diagram.
Well, if it's frictionless, there's no force of friction.
Yeah.
And it could be the very high-end learner and the struggling learner, but it doesn't need to be that kind of transmission of knowledge.
Well, A equals delta V over T. Is the velocity constant?
Yeah. But I'm not sure why.
Just the dialoguing is really enough, usually, to make sure that education happens.
No, it's acceleration of gravity. You're saying no, right?
Yeah.
Would you care to explain it again?
And an important piece of the structure is for students to make that aha moment that oh yeah, you know, if I just dialogue it with my peers, and if I really apply the rules and the big ideas, we can actually figure this out ourselves.
Yes. Actually, no.
Why?
Because you're applying a force. So if you apply a force, you always have an acceleration. So it wouldn't be possible.
So you have more than one student looking in on a problem together. Usually 2 or 3 is the good number. And as a teacher, you can circulate, and suddenly, instead of having to look down and see how their process is going on this tiny sheet of paper, it's blown up to life size. So as a teacher, you can see from a distance what suggestion, what question, what hint. Now let's say the marker is falling, right? Falling towards the table, right? During the time that the marker is in the air, is it touching the table?
No.
Can the table influence the marker when it's not touching it?
No.
Okay, so is the table able to apply that normal force to that falling marker?
Scientists use this all the time. This is the way scientists operate. But it gets kids excited about it because they can't get their hands on it, but they can get their minds on it.
There.
And they can relate what's in their minds to what they're doing with their hands. And that gets kids excited.
I think we're going to go forward and we're going to have our board meeting. So here's what we're going to do. We're all going to try to get into some kind of configuration where everyone can see everybody else's board. Remember what we did last time?
Julian's group is the only group that shows that gravity force is getting stronger as it gets closer to the ground.
And you have, at the end, instead of a student being asked to go to the front of the room, you can now democratize and say, okay, everyone's done with their problems. Let's all see each other's problem.
Technically, the closer you get to the object, it is going to get stronger. But since the reference frame is like just a ball being dropped, it's not getting stronger.
That's part of it, Brian. I'd rather step into the role of the facilitator of the experience, not the sole source of knowledge. So when we're configured in some kind of circle where everyone can see everyone else, and I'm actually removed from the circle, I'm communicating to them that I'm not the central point of attention, that it's all from that shared community, and that there's no one perspective that's the important one.
If your hand is moving at a constant velocity toward the block and then applying that same force, the continuous force, then yes, the block will be moving at a constant velocity as well.
Speed of, let's say, like 60 miles per hour, it's not accelerating, and it has a net force of 0.
Then you would have to have...
If they're talking to each other and if they're correcting each other, they're reinforcing what the big idea is, but it's also getting understood by their peers.
Inertia is not a force. Inertia is just a measurement of how likely an object is to move. So I don't think it's right to put it in a force diagram.
Because inertia, as he said, is the ability for something to be able to move, and its likelihood to do that. And the ball doesn't change its inertia because its mass is staying constant. And also, it doesn't belong in the force diagram because it's not a force. So I agree with that.
Because whatever words I use, I don't expect that they as easily go through. But when they hear it from a peer and when they hear it from 5 other peers, somehow that kind of starts to make a little bit of sense. Because it's not coming from the authority of me, it's coming from the common sense and the shared previous experiences of peers.
So, well, obviously, if you get to the top of something, you're assuming that, like, now it's 0. Well, there's a change between where you were before and when it's 0. If, like, you're accelerating.
Isn't acceleration also constitutes the change in direction? So when it gets to the top, it would have to start dropping down.
Which is exactly the change idea that John Corey was talking about. And now you're saying we can share in that positive experience, or we could even critique each other and say, in a very low accountability way, you know what? There's 3 groups who had this answer, but one of them's not exactly like the others.
They say yes. They say no.
Now, either they were on the right track or they were on a wrong track, and instead of being the teacher who says, let's aim at these kids, the kids can figure it out. And the kids have the conversation. And ultimately, they're learning a lot more from having that conversation than they are from you telling them what the right answer is. So you never have that one kid who doesn't do any talking, because maybe they're afraid of talking in front of 30 people, but in a group of 3 kids, they don't have a problem talking. So you have every kid have something to say, and it's meaningful. You have everyone who's done some practicing with stuff. You have everyone who's had a chance to present and be the important person, and you've been able, as an instructor, to be able to have eyeballs on everybody doing some kind of problem in a meaningful way.
But it does require work. It does require active engagement with the students. You can't just stand behind the desk and give a lecture and put the theories and the laws on the board and the equations on the board. You have to have the students working on it and developing it.
Is it possible to have constant velocity?
Yeah.
And you were the one who said we made this more difficult than it needed to be, or more complicated.
I feel like...
Let's go back to the yes or no. Is it possible for that situation to have constant velocity?
I feel like yes.
I mean, many teachers use a blend. There are people who are purist, that the students have to discover everything. I think that's a little too demanding. It took us, 5,000 years to develop physics the way it is now. It took Newton until 1786, over 50 years of his life. A genius, one of the supreme geniuses, to develop Newton's laws. I don't think a kid is going to do that from scratch. I think the teacher has to provide a lot of guidance. And the teacher has to provide selected, intelligent guidance. That's the key thing. And then he has to know when to get his hands off and let the students explore. He has to get that right question in there, or supply the right answer. Sometimes the teacher has to supply the right answer.
All right, that's what's going on in the space station. All right? Okay. I think that's an okay place to leave it for today. What you want to have them do is always look to you as a guide to help them understand, but never as the source of all information. Understand that they can get that from themselves. So you're not going to be around after the course ends. There's no textbook that they can look in the back pages of to decide whether this assertion about the world is true or not. But as long as they can turn inward and realize that they have that strength, then you've given them something that can last for the rest of their lives, not just till the end of your class.